right, so this was the problem, and you were focusing on this right here. Are other people able to join with audio? If you don't want to do video, I guess that's okay, but it's going to help if you can ask questions and stuff. So are other of you on with audio?
I was about to say, it seems like everybody seems to be muted for some reason.
Yeah, Colin is the only one I can hear. Anybody else?
I can hear you all. I'm deciding not to talk.
Okay, all right, okay. So I just want to make sure that it's not a setting of mine that's I'm screwing you guys up. Okay, so the quiz was for this, for 7 to 9 in X, and 4 to 8 in Y. That was the region, so I kind of isolated that. And then the first question was dA. And dA is going to be the area of each individual square. So these are 2 by 2s. So dA was 4. 2 times 2. And then I said upper left corners.
What's that sound?
Someone's moving a computer or something. So we said upper left corners, and so then we're going to pick off the values of the 4 squares in the upper left. So it's going to be 2, and this is going to be 3, and this is going to be 4, and this is also going to be 3. So the four G values of G are 2, 3, 3, 4. So 2 for this one, 3 for this one, upper left, 3 for this one, upper left, 4 for this one, upper left. And then if you do the math, you're going to do 4 times 2, 4 times 3, 4 times 3, 4 times 4. So we're doing the double integral over R of G dA. So we're summing up 4 of these. So we're going to take, these are the values of G, and this is the value of dA. It's going to be 2 times 4 plus 3 times 4 plus 3 times 4 plus 4 times 4. And so that came out to 48. Questions on the first problem, which was the first 3 questions on the quiz. Anybody got a question on those? Okay, I guess we're good. So then the next question was, it was pertaining to the volume underneath x squared plus y squared. And then over the triangle y from 0 to x, and x from 0 to 1. So that first question was, what do you need to do this volume? And it's a double integral. First of all, double integral. And the next question was, what's the first antiderivative that you're going to do? So first antiderivative will be this with respect to y. So the antiderivative will be x squared y plus y cubed over 3. Because it's like partial antiderivative. You're doing antiderivative considering x to be constant. So this will be x squared y and then y cubed over 3. And then when you do the math, this whole thing, plugging in 0 and x and subtracting, you get 4/3 x cubed. And now we're integrating that from 0 to 1. And you get 1/3. Questions on the volume problem? Oh, sorry. Yes, you get 1/3. That's right. Questions?
Why don't you just split up the integral and solve it when you're done taking the derivative for x?
Taking the derivative for x.
If you're taking the partial derivative for x, wouldn't you then just split it up and solve it, keep it in the separate components? Like
these two?
Yeah.
You can. Yes, you can. That will work. What you get here is you get x cubed plus x cubed over 3. So you can evaluate those separately, but I noticed they were both x cubed terms. So they're like terms. So I made 4/3 x cubed. But okay, if you evaluate it as a sum, you'll get the same answer.
Mm-hmm.
Does that make sense?
Yeah.
Anybody else? Questions on the quiz?
None that I can think of.
Okay, so so with the online format of the quiz, with using Canvas, I'm going to try to take one question and break it up into like 3 or 4 questions so that you have some chance for partial credit rather than just the final answer. So I hope that helped a little bit. All right, I want to talk about exam 2 because we're going to do a retake for exam 2. And so let's find that here. So I think, you know, going through this, it's been a long time, almost like probably a month since we took this exam, and it didn't go as well as some of you had hoped. And so we really need to review these principles and concepts and problems. So let's take the time to go through the exam. Please speak up and ask questions whenever you have them. There we go. But just we're trying to remember all this stuff that we learned such a long time ago, because we're going to take a retake, whether that's this Thursday or next Tuesday. We can talk about that, but we just want to refamiliarize ourselves and be as ready as we can for the retake. So here's the first question, and it's talking about, this is a level curves for some surface. Sorry, mine.
Would be a cone, wouldn't it?
Okay, so question is it could be a cone, could it be a sphere or a paraboloid? So the key to this question is the fact that the circles are equally spaced. So what does equally spaced contour lines mean as you move along equally spaced contour lines? For the same distance you go horizontally, your change vertical change stays the same, right? Each contour line is like a vertical height. It's a z value. So as you're changing horizontally, your z value keeps changing by the same amount for the same horizontal change. So what kind of surface would that be?
We have someone here, David, saying linear, so it should be C.
Right. So yeah, so you have constant rate of change in the z direction. So we've got these concentric circles, you know, with constant rate of change, which means that the sides of this surface have to be like linear sides. A half sphere would have a different distance between the contour lines, right? So your contour lines here would be a lot closer together than your contour lines here, because your rate of change is higher where the graph is steeper, and then the rate of change is lower where the graph is more shallow. So you'd have, and same with a circular paraboloid. So for these two, you won't have equally spaced. You'll have concentric circles, but they won't be equally spaced. So answer to 1 is C, circular cone. So just shout out with your questions if you have any. Okay, what about this? Now here I'm giving the graph and saying, what will the contour plot be like? So if you took any level, right, any z value, so say this is z equals 3, what will the level curve on this ramp thing be? Will it be, so it's talking about lines and exponential curves. Will it be a line or will it be an exponential curve when you look at a particular level of this surface? So it's going to be a line. Okay, so when you cut a horizontal plane through the surface, your contour is going to be a line, and the same with every plane that you pick. So you're going to get lines when you cut horizontally through this thing. Okay, you're going to get lines. So you won't get exponential curves. You could get exponential curves with vertical planes, but then those wouldn't be level curves. Level curves are for constant z values. All right, so we're not going to get exponential curves. So it's either non-equally spaced lines or none of these. So will they be non-equally spaced? Yes or no?
It would be non-equally spaced because it's exponential. Like it'd be more clustered together around the bottom part. That's a bit more level to the plane.
So where the surface is shallower, are they going to be closer together or farther apart?
In my opinion, I think they would be a bit closer apart. But then as you go up further, like you're increasing more, so wouldn't that be farther?
Yeah, so if your z values are constantly spaced, then your lines are going to be closer together where the surface is steeper, and then further apart where the surface is more shallow.
All right.
So so this is gonna be D, non-equally spaced lines. Any questions on that one? Okay, so then here I gave you, and there's an intersection. This is y equals x squared plus z squared, and we know that. Remember, that's a paraboloid opening on the positive y-axis. So this is that, and so then I'm taking all these other curves and saying what's the graph of intersection with each of these with this kind of base reference curve or reference surface. So x equals 2. So there's kind of two ways to do this. You can make pictures and imagine what's going on, or you can actually do the math. So doing the math here for x equals 2 and y equals x squared plus z would be y equals 2 squared plus z, and what is that?
Y equals, let's say, would be a parabola.
Yeah, that's a parabola, right? And if you imagine the plane x equals 2, which is two units out in front of the screen, intersecting this thing, you're going to get, a parabola like this. If you intersected a plane through this paraboloid. So this one's a parabola. Y equals 5. So if you read on Canvas about what I did to get your score, is I took the better of your score on the whole test and your score on what I called the core items, and that was 9 questions that were principles that were heavily emphasized and were a good distribution of all the concepts and weren't really like hard, tricky questions. I thought they were kind of straightforward questions that were really foundational to what we emphasized in class and the homework. This was the first one of those. Number 4 was, what would you get when you intersected y equals x squared plus z squared and y equals 5? So,
in case you missed, I'd probably say a cylinder in this one.
Okay, but a cylinder is not a curve, right? A cylinder is a surface, right? So here's y equals 5. And you're going to cut it through that paraboloid, and what will you get?
You'd get a circle.
Yeah, you're going to get a circle, and then again the math matches up. If you combine these equations, 5 equals x squared plus z squared, and that's a circle, right? That's the equation of a circle, and that's that circle right there at y equals 5. Okay, so that was number 4 was the first kind of core question that I computed a second grade on the test for you just based on the 9 core questions, and I gave you the higher of the 2. Okay, so then number 5, y plus z equals 1. So what would y plus z equals 1? Again, here's the paraboloid. Y plus z equals 1 would be a plane like this. So what kind of what would you get if you cut a plane like on an angle through a paraboloid?
An ellipse.
That's an ellipse, right, Kyle? So that one's an ellipse. Last one, x squared plus z squared equals 1. So basically you're taking a paraboloid that keeps getting bigger and bigger and then intersecting it with a circular cylinder on the y-axis. So what are we going to get when we intersect those two? So we got this paraboloid opening on the y-axis. This is a circular cylinder parallel to the y-axis. So what are we going to get for that? So it's going to intersect right here. And you're going to get another circle for that.
Circle.
Okay, so do I need to be checking the chat for questions?
I think you just need to be checking them for answers just in case, because David's spoken like
I don't know if I can see both at once. See if I can see this.
Oh, wait, that's...
Yeah. Anyway, okay. All right, questions on these 3 through 6. So we got a parabola, a circle, ellipse, and another circle. Any questions on those? Okay, moving on. All right, so partial derivatives. Remember we said the meaning of a partial derivative. So this is a function. The C function gives a level of oxidation on a rectangular plate, where x is like the distance to the right and y is distance up. So we could kind of draw a plate with the x and y axes. So here's our plate, and so if you put the origin on the lower left corner of the plate, then it's just like x and y coordinate is your location on the plate, because x is distance to the right of the left edge, and y is vertical distance from the bottom edge. So x and y coordinate is just your location on the plate. And so what would, if C is the level of oxidation, what would the partial derivative with respect to x be? So remember we worked on this. What do you say? Given, so this means given a what? Small change in x? Given some dx close to 38. Right, so we're at the point 38 here, say over here. And we're going to make a small change in x. And this partial derivative is going to, it'll tell us what the change in oxidation is. So dc will equal whatever that value of the partial derivative is times as much as that small change in x. Remember this? So given any small change in distance along the plate to the right, the corresponding change in oxidation will be the partial derivative times the change in x. So it's giving us a feel for how fast the oxidation changes relative to x, right? If this is a big number, then multiplying it by this change in x, you're going to get a bigger change in oxidation. If this is a smaller number, you're going to get a smaller change in oxidation. This is rate of change, right? Rate of change. So if you read through these, here's your key. So moving a bit right from 38, that's good, right? That's our dx. It says the oxidation level changes minimally or not at all. And that's the fact that that rate of change is 0. Rate of change of 0 means for a small change in x, your oxidation is going to stay the same or change just a little bit maybe, or not at all. So the right interpretation of that partial derivative being 0 is this answer D. Questions on that one? And then the rest of them, I guess one that's been popular in the past, let's see. So this no oxidation exists at 38. That would be just C of 38 equals 0, right? So this is talking about the rate of change, so it's not A. Yeah, I think sometimes people like the answer C, but the problem with C is that would be talking about like starting from here all the way to here. But partial derivatives or rate of change is like a local phenomenon, right? So if I have that Cx38 is 0, that only pertains to right around that point 38. And this answer C is talking about everywhere from the lower left corner up to that point. And so that doesn't work, because a partial derivative is just a value of a partial derivative is just a local phenomenon right by the point in question. Okay. Stop me if you have a question. All right, now this one, same situation. And now we got the partial with respect to y is 5, and we know the value of the oxidation at 2,9. So again, we got our plate. And say we're at 2,9, right here, say. And we know the rate of change with respect to y now is 5. That means moving up a little bit to get the change in oxidation. You're going to multiply your change in y by 5. So dc equals 5 times dy. Given a small change in y, the resulting change in oxidation is going to be 5 times that change in y. And we also know that the oxidation itself is 75 there. So we did problems where we picked a small change in y, and then we said, let's estimate what the new oxidation, in this case, the new oxidation is. So here, the level of oxidation on the plate at 9.2. So what does that indicate for dy? From 2.9 to 9.2, dy is 0.2, right?
Yeah.
So if dy is 0.2, then we can estimate the change in oxidation that you would get for moving from 9 to 9.2, which is 5 times, the rate of change is 5 times that change in y. So 5 times 0.2 is equal to 1. So this rate tells us that our change in oxidation for a change of y of 0.2 would be 1. And so since it was 75 here, then it would be 76. So A is correct. Because this is implying a change of y of 0.2. From that we can get the change in oxidation, which is 1, or 0.2 times 5. And then we can add that 1 to the 75 to get 76. This one is not right. So if y changes a little from 2.9, the rate of change changes by 5 times as much. That's not right because the rate of change tells us how the original function value changes. So the rate of change changing, this would be like cyy. It'd be like the second derivative would tell us how the rate of change changes. But the first derivative tells us how function values change, or in this case, just the plain old oxidation. So this idea of how much does the rate of change, well, that would be if cyy was 5, the second derivative. So that's not right. Okay, any questions on these plate problems, oxidation?
So.
All right. Okay, number 9 was the next core question for the core exam. And so this was kind of a theme that we've struggled with. What kinds of functions give us surfaces in space? And what kind of functions give us curves in space? So from a lot of your answers to these questions, we didn't really have that down. So what gives a surface in space? What kind of function or equation gives a surface in space? So for instance, all these are surfaces, right? Y equals x squared plus z squared. Y plus e equals 1. X squared plus z squared equals 1. These are all surfaces. Here's a surface. Z equals e to the y minus 2. All right, those are all surfaces. So what gives a surface is, was someone going to say something? A single equation of x, y, and or z. Okay? So a single equation of x, y, and or z is what graphs as a surface in space. Okay? What graphs as curves in space? How do we get curves in space? So remember, several times we worked on, remember my favorite function?
Yes.
Right? We did this several times in class, right?
We did, yes.
Okay, and that was how I introduced vector functions, right? And then we worked on vector derivative functions and acceleration, and we kept going back to this function and others. And so a curve in space is a vector function, right? Or a parameterization, right? X as a function of t, y as a function of t, and z as a function of t, which you could write as a parametric set of parametric equations, right? X equals f of t, y equals g of t, z equals h of t. So a vector function or a set of parametric equations gives a curve in space, right? As t changes, each t gives a vector. And then we put all those vectors in standard position at the origin, and then let t change, and those vectors kind of like sweep out like a laser light show, sweep out a curve in space, right? That's our vector functions. And then our surfaces in space are planes, paraboloids, spheres, cylinders. Those are all a single equation, one equation of x, y, and or z together. So if there was something, so if you had your wires crossed on this, I hope that kind of straightens it out once and for all. Okay, so this one. So I give you this function here. RT, 2t squared, t minus 1, and radical t plus 2. What best describes the graph of that function right there?
Well, we have one answer saying that it's a line in R2.
So remember that a line was specifically, when we did lines were what? X is, okay, I gotta turn this on and off again here. All right, let's see if that works. Okay, so a line would, remember a line specifically, yes, a line is a type of vector function, but specifically it's when you have, let's say, x naught plus at, y naught plus bt, c naught plus ct, or z naught. So remember you had a point on the line, and then you had the ABC was your direction vector of the line. So to get a line in space, you need all three individual components have to be linear. So you get a linear function, linear function, linear function, which comes from their point in space and the direction vector of the line, ABC. So would this be a line? Would this be a line? So it's not a line because I got a t squared, I got square root. That's, we know in R2, those kinds of functions give curves, right? So we're talking about a curve in R3. So nonlinear curve in R3 is what you get for this. This is like the loop-de-loop, right? This is like the roller coaster function. Like that. Okay, but I mean, it's going to be different than that, but this is the idea that if you let one or more of your components vary without constant rate of change, without being linear, then you're going to get a curve in space. Okay, so 9 was D. All right, so then consider the normal plane to that. So remember with the normal plane, what vector defines the orientation of the normal plane? So I'm just going to draw like just a random curve here. So pretend that this is our RT function. All right, so I want the normal plane. So let's say that's like this right here. So what vector is going to define the normal define the normal plane at a particular point, normal to the curve? So is that the tangent vector, the normal vector, or the binormal vector?
I was thinking tangent vector.
That's right, and that's what we remember. We kind of said it's the tangent vector is orthogonal to the normal plane, and the normal vector, if you remember this, was orthogonal to the tangent plane. So it's kind of they're flipped. Okay. So what do we want? We want the tangent vector. To get the defining the orientation of this plane, we need the tangent vector to this. To get the tangent vector, we need the tangent vector is from the rate of change vector function. So it's going to be 4t, 1, and 1 over 2t plus 2. So what we need is which vector is this for the t. So then we need the t value for this point, right? So we have this point, say 2, negative 2, 1, right there, 2, negative 2, 1. And so in order to get the tangent vector, we need the t value corresponding to 2, negative 2, 1. So we can look up here. So what gives 2, negative 2, 1? Well, the easiest thing to look at is the y-coordinate. What t-value gives negative 2? That'd be t equals negative 1. And we could check the other ones. 2 times negative 1 squared is 2. Square root of negative 1 plus 2 is 1. So that works. So we're talking about we need the tangent vector at t equals negative 1. So we're going to plug that in. So we get negative 4, 1, and 1 over 2. So that is this one. Answer D. So for this one, you need to remember that the tangent vector is what defines the normal plane, because the tangent vector is orthogonal to the normal plane. And then we need to get the t-value for this point in question, which we figure out what t-value gives these coordinates. And to get the tangent vector, we're going to use the derivative or the rate of change vector function. Any questions on this one?
Other than just how disappointed in myself with some of these questions.
Okay, yep. All right, so now I just want to talk about the tangent plane. So the tangent plane, what vector defines the tangent plane? So say I got this point right here, and I want the tangent plane to that point. So what vector is going to define the tangent plane? In other words, what vector is orthogonal to that plane relative to the curve? Is it T, N, or B?
Let's see. Would be N.
Right, it'd be N. So the normal vector to that curve is what's orthogonal to the tangent plane. So if this is the tangent plane, then remember what our normal vector is, the ABC. So we have the vector 1, 2, 3. That must be the normal, since it's the tangent plane. That orthogonal vector to the plane must be the normal vector to the curve. So B, 1, 2, 3 is normal to the curve at P. Questions on that one? Okay, oscillating circle. So I gave you the oscillating circle is just this tangent circle that lies in the oscillating plane. So I gave you the oscillating circle. It was at z equals 3, 2 sine t, 2 cosine t, 3. So that lies in the plane z equals 3. So it's a horizontal circle at z equals 3 with radius 2. So this is for some curve C. Like this, at this point, say, this circle lies in the osculating plane. Remember, the osculating plane was the plane of the curve, like the plane. Like if you were to take a little bit of the arc, it's the plane that arc is in at that moment. Okay, and so that's our osculating plane. Our osculating plane in this case is a horizontal plane at z equals 3. And so the binormal vector, remember the binormal vector, was orthogonal to the osculating plane. So which one of these could be the binormal vector? Well, it's going to be the vector that's orthogonal to the plane z equals 3. So which one of these is orthogonal to z equals 3? Well, that'd be k, right? Because if it's z equals 3, then it's going to be an orthogonal vector is going to be in the z direction. So it's z equals 3 is k. Questions on that one? Oh, you guys are quiet. What would I do without you, Colin?
They're all muted.
Talking to my wall. Okay. Next one. We want the equation of the tangent line. Equation of the tangent line. So an equation of the tangent line is, again, it's going to be, so we could write it this way, x naught, and that's the way it's in the answers here, x naught, y naught, z naught plus t times ABC. So remember, that's a point on the line, and this is our vector parallel to the line, or the direction vector of the line. This could also be written like I did earlier, x naught plus AT, y naught plus BT, z naught plus CT. But the forms of these answers are this form. So what do we need? We need a point on the line, and we need a vector parallel to the line, or the direction vector of the line. So it says at point -5, 7, 3. There's our point. So this is going to be our -5, 7, 3. It's our point on the line. So that's just A, B, or E. So these are gone. A, B, and E have the point in the right place. And now we need the equation of the tangent line. So for the equation of the tangent line, does that use the tangent vector or the normal vector? Now this is the tangent line. This is the tangent line, right? So we want the equation of the tangent line. Is that going to use the tangent vector or the normal vector?
I want to say tangent vector.
Definitely, right? So the tangent vector is the direction of the curve, and that's going to be the direction of our tangent line. So for a tangent line, we're going to need the direction of the tangent vector, not the normal vector. Right? We don't want that. We want the direction of the tangent vector. So we don't need, this is not needed. So 1/3, 2/3, -2/3. And remember, it can be any constant multiple of this in your equation of your line. So really, we've got 1, 2, -2. So there it is. 1, 2, -2 is really the same, it's parallel to that. So this doesn't work, 0, 1, 1 doesn't work. That's actually parallel to the normal vector. And then 1/3, 2/3, what's wrong with this? Oh, this is the wrong point. So I took, this is not right, because this is not the point. This is the opposite of the point. This is -5. Yeah, so this doesn't work.
That one threw me for a loop for a second. I was like, is that a typo or?
Yeah, no, so this is, we're using the point in question. You can't take the opposite of the point, because that's a location. So you can't do that. So its answer is A. Questions on that one? Okay. I think it was 14. Yeah, 14 is the next. This was the next core question out of the 9 of them. So this is core question. Figuring out what the partial derivative is from the table. Okay, so we're looking at 4015. And remember, so that partial derivative with respect to v is going to be, generally, it's going to be height of waves. It's going to be a change of height per change in speed in knots. So we're estimating this ratio of the change in height to the change in speed. Okay, at this point. So we're holding t constant, and we're looking at changes in v. So that means this way, up and down. So a change in v here, and a change in v here. So here, v changes by 10. So v is changing by 10 each time. And when v changes by 10, how much does the height change? Here it changes by 9, and here it changes by 11. So we could average them. So on the average, the height of the waves is changing by 10. Therefore, rate of change is about 1. Here, the rate of change at this point is about 1. For every change in speed, you're getting a kind of equivalent change in wave height. Can everyone still see my writing?
Yes, I can at least.
Okay.
Yes,
So
I see.
this was the third core question, because we did lots of these. We did them on graphs, we did them in tables. So this was core question number 3. Any questions on this one? Okay, next. Can't get to my There we go. All right, so then using wow, can't. All right, there we go. So now using what we learned, estimate the height of the waves in feet resulting from winds of 50.6 knots blowing for 4.9 hours. So now in this question, we kind of have to put it all together. We're using changes in both wave height and time to predict a new, time and speed, wind speed, to predict a new wave height. So 50.6 knots, so we're looking here at 50.6 and 4.9. So right here, 4.9. So what we got to do is we have to estimate both partial derivatives at this point right here, and then we're going to let the speed increase by 0.6, and we're going to let the time decrease by 0.1, and then see how that changes the height of 19. So for a change, so for dH dV or FV at 55. Yeah, okay. That's going to be about what? Change in V is, so for change in 10, we get a change in speed of 5. So it's going to be 1/2. And then for dH dt, which is ft at 55, that's for a change in 5. We get a change in also 10?
10. Yeah.
Oh, so it's 10 over 5, right? So for a change in 5, of height, no, time, change of 5 of time, you get a change in height of 10. There we go. So that one's 2. Okay, so then we know what these numbers mean. Given any change in wind speed, the corresponding change in height is going to be 1/2 times that change in wind speed. What's our change in wind speed here?
0.6.
0.6. So our dV is 0.6. And our dt is negative 0.1, right? Because we're going to go we're starting here at 19. We're going to increase wind speed by 0.6. We're going to decrease time by 0.1. Okay, so then our overall change in height is going to be, it's going to be 1/2 times the change in wind speed, which we said is 0.6, plus our derivative times the change in time.
In this case, negative 0.1, yeah.
Right, so this will be 0.3 minus 0.2, is that right? Our overall change in height is going to be positive 0.1. And if we're at 19, then the new height is approximately
19.1.
19.1. Okay, questions on that one? So that was putting it all together, and we saw examples like that, but you had to know the whole thing. So find the partial derivatives, find the individual changes in speed and time, and then find the corresponding changes in height from each of those and add them together, and then add that change to the original. Any questions? All right, this one. So here we've got this cylinder. It's running in the x direction, and this is the functions f of xy for it. So asking about the second derivative at point Q in the y direction. So remember, that was how that tells you how the partial derivative with respect to y is changing. So if you look at Q here, color, let's see.
It looks like Q is just located on the x-axis.
So as y increases,
XZ plane.
as y increases, yeah, right. It's parallel. Yeah, it has a y coordinate of 0. So as y increases, what is the partial with respect to y doing? Increasing or decreasing? So it's going like this, or it's
decreasing.
Concave down, right? Concave down means the rate of change is decreasing, and therefore Fyy is?
Left double y is negative.
Negative, right? So if the rate of change is decreasing, or you have concave down, then your second derivative is negative, so we got to get the reason why. Z is decreasing, or the rate of change is decreasing? Which one? So the second derivative tells us how the rate is changing, right? So the second derivative is negative because the rate is decreasing in the y direction. So 16 is D. Concave down. Okay? The value of fx at point P. So at point P, for a change in x, how does z change? So as we move in the x direction, we're asking how does z change? Remember, that's going to be...
Doesn't really look like it's changing in this
Yeah, if
direction.
it's a cylinder. If it's a cylinder in the x direction, then you know for a fact that it's not changing, right? A cylinder in the x direction means, and moving in the x direction, you're not going to change your z value. It's going to stay the same. So dz dx is 0. So that's answer C for 17. Okay. If you have a question, don't hesitate to speak up. All right. The direction of the gradient at point P. So you remember when we were talking about the directional derivative, what was the direction of the gradient? It was the same as the direction of?
Dang it, I lost this one.
Wasn't it the greatest rate of change?
Right.
Like that?
Is that Max?
Yeah, that's me.
Yeah.
Max.
Right. Direction of greatest rate of change. So which way is the direction of greatest rate of change here? Is it, and again, that's a horizontal motion, right? Horizontal. So is it forward, right, back, or left? Greatest rate of change at point P. So which way would you step to go up the fastest? That's what we mean by greatest rate of change.
You go back, right?
Back would be like this.
Oh, and left.
Yes.
Left.
Straight to the left.
Left. That's right. So left is going to be our direction of greatest rate of change. So did I give them as, I don't know how I gave the answers. It's,
Max, I think you're starting to turn into a robot. I heard you lagging out for a second there.
all right, yeah, so I gave it both ways. So going to the left from point P, what direction is that? I gave it both as vectors and angles. So what direction is left in R3, like that?
Negative y direction?
Right, so that'd be negative j, and that'd be theta is 3 pi over 2, right? Because our theta of 0 is in the positive x direction, and then theta increases around this way. So this would be like pointing down in the unit circle, right? Which would be the negative y direction. So that's the direction of greatest rate of change, or the gradient. Okay? Okay, so a reasonable estimate for the magnitude of the gradient. And so, again, thinking about rate of change, the direction of the gradient was the direction of max rate of change, and the magnitude of the gradient was the magnitude of the rate of change, if you remember. So we're looking at, so we're kind of saying, like, what rate of change is that? If we just had to eyeball it, what would that be? So I think 0 was a choice, and there was a negative choice, and then I think like 1/4 and 2. So which one of these would be a reasonable estimate for that rate?
Are we going back up or are we still going down?
So the rate of change is like the change in z with respect to, and now it's like the change in the negative y direction. Right? So for a change in the negative y direction, how much does z change? That's our directional derivative. So this would be like 2, right? Because like for every, this is the steepness of this is like a slope of 2. Do you see that?
Are you looking at number 17?
No, no,
I think
19.
the question was number
19.
I think it was number 19.
Yeah, the value of fx is 0.
Okay.
Value of fx is 0. That's if you move in the x direction. So 19 talks about like what is the magnitude of the gradient at p. And so the gradient, remember the magnitude of the gradient is the magnitude of the greatest rate of change. And so that would be in this negative y direction going to the left. Your change in z per change in the negative y direction is something like, it looks like close to 2 to 1. Well, there's no other answer that's anywhere close to that. So it has to be 2. Yeah, because it's not negative, it's not 0. So it's, you know, the gradient's going to have a positive value. It's definitely not 1/4. It's going to be 2. So it's like the slope of this surface in the negative y direction. So 2. Okay, now suppose an ant moves a short distance on the surface such that its x-coordinate decreases as the y-coordinate increases. What could be equal to the directional derivative according to the associated with the movement of the ant? So if his x-coordinate decreases, that's going back. If his y-coordinate increases, that's going right. So it's going to be both of those together. So the direction that the ant is moving is this way. So what will happen if the ant moves kind of back and to the right, but stays on the surface? How will the ant move? If the ant is moving this direction, what can you say about the ant's movement?
It is it can be represented by a vector, technically.
Well, I'm just talking more about like, how could you describe what's happening to the ant as he moves in that direction? Back and to the right on this thing. So just kind of from a like really elementary kind of conclusion.
Do you mean that he's going down the hill?
Downhill, right? Downhill. So yeah, so going simultaneously right and back into the screen, that would be downhill. So what could we, if it's downhill, that means z is decreasing. That means dz is less than 0. So what could we say about the rate of change in that direction? The ant's going downhill, the rate of change would have to be?
Negative.
Negative. And there's only one answer that's negative, right? So which could be equal to the directional derivative associated with the movement of the ant? Only a is a negative value. So that's the answer to that one. Okay, any questions on this page with this graph here?
I think so. Someone else has something they want to say.
All right.
Could you actually go back to that one?
Yeah, sure. The last one?
Yeah. So the answer for E, I think if I remember right, I think I put E for that.
Yeah. So what is E?
But I'm not sure why.
What is that? So yeah, that's describing what? That describes that.
That would be a vector, yeah.
Yeah, that's
So,
a vector.
It's a vector.
That's describing the x-coordinate decreasing and the y-coordinate increasing. So that's like the unit vector of his motion. Right?
Okay.
This question is asking what could be equal to the directional derivative, which is what? The rate of change in that direction.
Okay.
You see the difference?
Yeah, I don't remember what I put for that, but yeah.
So
That makes
remember,
sense.
yeah, so this is the rate of change in the direction of u, and that was what? The gradient dot u. Remember, that was how we calculated it. We got the gradient, and we did the dot product with the u vector. So this answer, yes, it pertains to this situation, but it's the u vector. It's not this, which is rate of change.
I have a feeling that those symbols are the symbols that represent it are very appropriate for the situation, because I have a feeling that many people made the exact same mistake.
Yeah, but it's not only is it fu, but I'm saying the directional derivative. The directional derivative, that's derivative, right? That's not a derivative. That's a vector of direction. So yeah, the derivative is the rate of change. That's what you get when you do the dot product of the gradient with the unit vector, if you remember doing those problems. That's the derivative. Does that make sense, Jake? That was Jake, right?
No, I think that was Jake.
Yeah, okay. All right. Okay, cool. Moving on. What's my next core? Oh, so the 21 is the next core question. So this was another core question, number 21. So we got a particle flying through the air, and at t equals 4 seconds, I'm giving you the tangential component of acceleration and the normal component of acceleration as their vectors, right? So this thing is flying through the air, and say right here, it has a tangential acceleration, which is what? Speeding up and slowing down. And then a normal acceleration, which is what the acceleration due to turning. So you can think of this as like the AT vector, and this is the AN vector. And so the question is, how do we get this? What's the second derivative? Well, the second derivative, that is the acceleration. That's all of it. So how is the acceleration? How do we get the acceleration from the tangential component and the normal component? What do we do to get acceleration from the individual components? So let me...
Cross product?
Nope. So let me make... Let's see.
Wouldn't it be the dot product? Oh, wait. Hold on. Dang it, I keep forgetting what the equation is.
Yeah, so these are the two components of acceleration. So, and then the second derivative is the whole acceleration. So what do we do with components to get the whole vector?
It's D. I'm dumb. Would add them.
Yeah, you just add them, right? That was a big theme that we talked about. You're just gonna that the second derivative is this kind of weird vector, but if we separate it out into its two components, we can make a lot more sense of what's going on, because sometimes it's all speeding up and slowing down, and sometimes it's all turning, and sometimes there's a combination thereof. And since these are orthogonal to each other, then the whole of the acceleration is just the sum of the two. So and that's what the second derivative is. It's the whole acceleration all combined together. So it becomes the sum of its components. Okay, going on to the next one.
Professor,
yeah, sure.
If you don't mind me asking for a second.
Yeah.
I don't mean to sound rude, but I seem to recall you saying something about wanting to max it out at 345 for the meeting length or something.
Yeah, we'll see what we want to do here. So we could pick this up Thursday. Yeah, because 3:45 is like the end of class. So, but I think we only have this page and the next page, and then this last page is all those surfaces. And I wasn't planning on going through all of those, just maybe the core questions from that. So I think we're going to be fine to make it in the next 15 minutes. But yes,
I just wanted to like.
Yes.
I just wanted to make sure because we were approaching that time and I wasn't sure how we were going to.
Yes, I think we're going to be fine to finish. Okay. Suppose you want to write the equation of the plane parallel and contain the particle motion at t equals 4. So which plane is that talking about? That's the key to this question is you want to write the equation of the plane parallel to and containing the particle's motion. So that is which plane? Is that tangent, normal, or oscillating plane? Containing the motion. That's the osculating plane, remember? Oscillating plane is like the plane that the curve is in at that moment.
At the moment, yeah.
Yeah. So, and remember the oscillating plane, how do we get that? That's, or the binormal vector is the defining vector for that, and that was t cross n.
That was the cross product one I was thinking
right.
of.
So since this is just in the direction of t and this is the direction of n, then we can cross these and to get the same direction as the direction of b. So for 22, it's going to be c. So that will give the same direction as t cross n because t is in the direction that the tangential acceleration is in the direction of t, the normal acceleration is the direction of n, so the cross product will be in the direction of b. And then that will define the oscillating plane. Okay, what three always have the same direction? What three always have the same direction? So the direction here is the tangent direction. So r prime will be in the direction of the tangent, t will be in the direction of the tangent, and at will be in the direction of the tangent. Those are all pointing in the direction of the curve. The first derivative, this is the unitized version of that, and then at will have that direction too. So we're looking for 2, 3, and 7. Where's that? Or sorry, 2, 4, and 7. B.
Yeah.
Those are all in the direction of tangent motion. Okay. Last question on this page. So that was that question was to kind of help you with this one. That was trying to get you in that mindset. If we want the velocity vector, then that's going to have this direction. Velocity is in the direction of motion, right? So we can use this, since these all have the same direction and then the direction of the velocity, we can use this for the direction of the velocity. And then we know this, it says the speed is 6, so that's the magnitude. 6 is the magnitude of velocity. So we have the direction from the earlier, up here. What is it? 2, 2, 1. 2, 2, 1 is the tangential acceleration. And that's going to be the direction of motion, so that's the direction of velocity. And then the magnitude is 6. So this goes back to this question we've seen many times in the course. Write a vector whose magnitude is that and is parallel to that one. So what do? We do the unit vector and we multiply it by 6, if you remember that. So we want the unit vector in that direction multiplied by 6. So this is square root of 9 is the magnitude. So we'll have 2/3, 2/3, 1/3 times 6. So this is the unit vector in the direction of that times 6 gives you 4, 4, 2. Okay, questions on that one? Okay, very good. And last page, or kind of. All right, the gradient vector is the partial derivatives. So it's remember the gradient vector is the vector of partial derivatives. So the partial with respect to x is 2e to the 2x cosine y. Partial with respect to y is negative e to the 2x sine y plus 1. So the gradient will be what you get when you plug 1 in for x and pi over 2 in for y. So pi over 2 makes this 0. Cosine of pi over 2 is 0. So this one is where we, so the y coordinate is e to the minus 2 times 1 plus 1. So 0 comma 1 plus e to the minus, oh sorry, not minus 2, is negative the plus. So it looks like 0 and 1 minus e squared, right here. Oh, this was a core question. This 17 was, or 25 was another core question. The gradient is finding the partial derivatives, plugging in your x and y. And so then you get 0, 1 minus e squared. Okay, and so then you can verify that at 0, 0, for the next question, at 0, 0 you get 2, 1. So you plug in 0, you get, that's right, you get 2, and 0 will give 1, right? So that's check. All right, so given that the gradient is 2, 1, what small changes of x and y together would increase f at the highest possible rate? What is that? That's the direction. Highest possible rate is the direction of the gradient. Right? The gradient tells you the direction. Well, this is the gradient. So if this is the gradient, we want to go in that direction. That means that for every change in x, we're going to change y half as much. Right? So these are changes in x. For a change in x of 2, y changes by 1. So by increasing x and increasing y half as much, we're going in the direction of the gradient, which is going at the direction of highest rate of change. Okay, I'm going to leave it up to you to stop me if I lose you, okay? Please ask questions. You can pipe in anytime. There we are. All right. What is the rate of change? All right, so this is, again, this is the gradient gives the direction of rate of change. And what the magnitude of the gradient is the magnitude of the greatest rate. Or the right, so the gradient gives direction and magnitude of greatest rate of change. So if I want what is the rate of change in the situation, meaning what is the greatest rate of change, then what do? I'm going to find the magnitude of the gradient, which is square root of 5. From the same point, you make a small and equal decrease to both x and y. What would the rate of change be in that case? So if it's asking for the rate of change in a certain direction, this is asking for a directional derivative. And so that's the gradient, if you remember, dot the unit vector. So our gradient is given as 2, 1. We have that. And we're going to dot that with the unit vector, which we get from this, a small and equal decrease to both x and y. So what unit vector represents a small and equal decrease to both x and y? So how do we get a unit vector with equal negative values? If you think unit circle, it's going to be negative radical 2 over 2, negative radical 2 over 2. So that's your unit vector. That gives a small and equal decrease to both x and y. when you do this dot product, I think you get this. 2 and 1, yeah. So this number 28 is just applying the formula for the directional derivative. You got the gradient, and you figure out the direction of the unit vector, and then you get this value. 7. Okay. So now, as y increases near 0, 0, the rate of change of y with respect to y. So we're asking if the rate of change increases or decreases, then we're asking about the second derivative with respect to y. So we need what we're asking about is fyy. So let's get the function again. E to the 2x cosine y plus y. We need the second derivative with respect to y. So e to the 2x. Is that right? We'll do this so it's not right. Yeah. Okay. So we need the second, if it's asking about if the rate of change of y is increasing or decreasing, that's the second derivative. So f of y is negative e to the 2x sine y plus 1. And the second derivative is, that's going to be negative e to the 2x cosine y at 0, 0. So that equals negative e to the 0 times cosine 0, or negative 1. Okay, so if that second derivative is negative, then what is the partial with respect to y is decreasing. So the rate of change of f with respect to y, because the second derivative is negative, that decreases since fyy is negative. Okay, questions about that one? Okay, last page was, or the last 2 pages was all of, if you remember, was all the surfaces. And so again, besides testing your knowledge of surfaces, this was also testing your knowledge of the distinction between surfaces and curves in space. So which ones of these, let's make this smaller here. Still a little smaller. So which ones are surfaces and which ones are curves in space? So this first one, surface or curve? Surface or curve?
Looks like a curve because the or well, maybe surface because you're taking out the getting rid of the square.
Well, no, it's not because of that. Remember, our surfaces are a single equation of x, y, and or z. And our curves in space are a vector function. So we got to remember this. Like today's the day. Let's learn this today. If it's a single equation of x, y, and z, x, y, and or z, that's a surface. If it's a vector function or a parameterized or set of parametric equation, that's a curve in space. Okay, so our surfaces would be this one. What's this? That's a curve, that's a vector function. This is a surface. This is another surface. And this is a curve. Or in this case, it's a line. Lots of you said this was a plane. This is not a plane. It's a line. X equals negative 2t, y equals 3 plus t, 4 is minus 3t. This is a line. This is a elliptical spiral. curve, right? It's a curve. Elliptical because you have different coefficients, and a spiral because you go around this ellipse, but then y increases as you go around the ellipse, so that makes a spiral. Okay, so I just want to talk about the two core questions I said were 35 and 37. So 35 and 37 were core. That's what I just said. So 35, it's an elliptical spiral, which I just explained. 37, so what is this? X equals y squared plus c squared over 9. So first of all, it's a surface. It's a single equation of x, y, or z.
Yeah.
What kind of surface is that? X equals y squared plus z squared. That's a paraboloid. And is it circular or elliptical?
Elliptical.
Elliptical, because we have different denominators. So yeah, so 37, we got an elliptical paraboloid opening up in the positive x direction. And then here we have an elliptical spiral spiraling down the y-axis as an ellipse. So those were the last two core questions. Okay, so we're just about out of time. So what I'm going to do is I'm going to post, so we need to decide, do we want to do the retake this Thursday or next Tuesday? So probably, I'm thinking probably next Tuesday. So we'll do the retake Tuesday. I tried to trim down the study guide as much as I can. I made a new study guide, and I tried to trim that down as much as I could from the original one. And then I also put, now for the retake, includes a bunch of practice.
Mr. Ashford?
Yeah,
Were you recording this? And if so, can you post it then on Canvas so we
Yep.
can review it?
definitely. I am recording, and I will post it. So we'll do the retake Tuesday. The study guide has been posted for a while. Like I said, it includes practice. And then hopefully this going over the test has kind of conjured up all these ideas again, and you can make some good progress on the study guide. But in addition to that, we'll have new material. So I'll post lecture videos for to review before Thursday, and then we'll do Wednesday office hours here in this Zoom room, 1:30 to 3. And then Thursday here from 1:30 to 2. And then the quiz will be at 2. On the new material for the...
Thursday?
What's that?
Do we have homework for Thursday?
Yeah, you're right. So there'll be homework. There'll be a shorter homework, and then the, of new material, which you get that from the lecture videos. And then we'll have the same deal where we'll have the quiz at 2 p.m. on Thursday on the new stuff. And to get your homework questions answered, tomorrow from 1:30 to 3, and then Thursday from 1:30 to 2, right before the quiz. And that's instead of me making a lecture video, or instead of a homework questions video. We're not going to do that anymore.